So welcome everyone, and in this video I am going to discuss about a special reagent, that is NBS, N-Bromosuccinimide. So this is N-Bromosuccinimide, right? So succinimide, which is brominated. Now this reagent has very good uses of in organic synthesis, and probably you may know the reagent for allylic bromination, but this reagent can be used as any brominating agent. Like you can use it for bromination of this double bond, it will form the bromonium ion, right? But the most common use of this reagent is the allylic bromination. And what is mean by allylic bromination? So let's say you have a substrate where you have a allylic position like this, or you have a benzylic position, so pH CH3, like toluene. So when you treat this type of substrates with your brominating agent like NBS, and in presence of light with some initiator like a radical initiator like AIBN, or you can so if you use light, no initiator is needed, and if you don't use light, then you need and you use heat, then you use this type of initiator. And in most of the books it is not mentioned, but a little amount of bromine, molecular bromine, is also needed to initiate this reaction. Okay, and out of this what you get allylic brominated product, like right. So this allylic or benzylic position is brominated. Now what is the mechanism of this reaction? So many mechanisms are proposed for this reaction, but which is most commonly accepted, that I will discuss here. So the radical initiators like AIBN, so structure of AIBN is this. So it is nothing but azo-isobutyl nitrile. This is the structure of AIBN. This is azo linkage, and this is azo linkage, and this is isobutyl group. So azo-isobutyl nitrile. Now what happens for this case is that when you when you heat it, it will collapse like this, and you get nitrogen plus this radical. Okay, now this is your initiator. I can represent it by I dot. So this is your radical initiator, and you have, I said that the molecular bromines are there in your reaction medium. So this initiator can attack on this molecular bromine, and it will create this bromine dot plus IBr. Right. Now you have your allylic. This is your starting material, and now this bromine dot can either attack on this double bond to give you this, or it can abstract a hydrogen from here. So Br dot can abstract a hydrogen from here, and that's how you get this radical. Now if you compare the stability of these two radicals, this radical will be much more stable because it has this resonance stabilization. Due to the presence of this adjacent pi electron, this radical is stabilized by resonance, and that's why this pathway is followed, and it is more favorable pathway. So this allylic radical will be generated. Now what can happen next is that, so this is your allylic radical, and in this step you are generating HBr, right? So this, what does this HBr do? So you have your NBS. This is your NBS molecule where you have this bromine. Now when you react NBS with HBr, this nitrogen pushes its lone pair, and this gets protonated. So this is your HBr, and it gets protonated. So in many textbooks they represent like this nitrogen is protonated, and you get here N plus, but it is not actually true because so I will tell you later. So first of all, you are getting this, right? So this one you get. Now in this step, this Br minus is generated. So this Br minus now attack here, and you are generating this one. Okay, this will be automation will take place. So this hydrogen will be on the nitrogen, and you will get this, and side by side you are getting this bromine molecule. Now you have this allylic radical and you have bromine molecule. So this allylic radical can attack on this bromine, and you are getting this product plus Br dot, right? So you are regenerating this Br dot in this step. So in the starting of the reaction, you use just a trace amount of bromine, and in every step when this allylic radical is generated, side by side this HBr is generated, and in turn this HBr is reacting with this N-Bromosuccinimide, and you are generating this bromine, which bromine react with this allylic radical, and it again generate a bromine radical. That bromine radical again attack on another allylic alcohol, another hydrogen, allylic position hydrogen, and it will generate another allylic radical. So in this step the bromine dot is regenerated. That is, it is a catalytic reaction, it is a chain process. And what is most important here is that in every case, after the abstraction of this hydrogen, this bromine little amount of bromine molecule is generated. So in your reaction medium there is no moment where your volume of bromine is very high. Always it is the ratio of this allyl radical and this bromine is 1:1. So their ratio is always 1:1. So you have one allyl radical and one bromine molecule to react, and that's why it will undergo this allylic bromination. What happens if you instead use large amount of bromine, right? So you can use instead this bromine, no use of NBS. Then what will happen is that this double bond attack here, and it will generate this bromonium ion, which will finally attack by this Br minus, and you will generate this ionic uh, dibromo product, right? So this mechanism is instead for so the purpose of using NBS is nothing but to keep the concentration of bromine ion low throughout the reaction, and that's how the reaction proceeds. Now these reactions are relatively simple. They give you this type of substrate, but one thing you have to remember is that if let's say you are given with this alkene and they give you NBS water DMSO, so water and DMSO. So in this case, if you don't know the actual role of NBS, then just looking at NBS you may write this product, so allylic bromination product. But in this case you have to look at the proper reaction condition. So you are using water, and in water medium what happens, your radical will not be generated, and in this case heat or light is not given. So the intention is not to generate radical. Instead this NBS can simply act as your brominating agent, so ionic brominating agent, and that's how this double bond will attack here, and you are getting this bromonium ion, right? And here you are getting this anion. Okay, so this bromonium ion you get, now DMSO is here. Okay, so DMSO can attack here, and you can get this one, right? After that water molecule can attack here, and you get this bromohydrin, right? So when water is given along with NBS, allylic bromination does not occur and you get bromohydrin. Other reaction can also be done with NBS, like let's say you have this substrate aromatic ring, and here you have another aromatic ring fused OMe group, and you react it with NBS. So you see there is no allylic position, and in this case it undergoes simple bromination. So you have your NBS reagent here, and so this will attack and you get simple brominated product, right? So you may thought that NBS is used as allylic brominating reagent, but you have to remember that it is not only a allylic brominating agent, but it is used as general brominating agent. And another one useful function of NBS is, so I told you about iodo-electronization, right? So let's say you have a double bond here and you have a carboxylic acid group here, and when you react it with iodine, first you generate this iodonium ion, and then this OH will attack here, right, to form this. So actually it will attack here because this 1 2 3 4 5 sorry, it will attack here. 4-membered ring will be generated because all exo, so it is Baldwin's rule. I will talk about it later. So according to Baldwin's rule, all exotate reactions are favored, and in this case this uh, 4-membered ring will be generated, right? And you are getting this product, so this lactone you will get, right? Now the same type of reaction, I told you that the reaction can also be done with any other halogen. And let's say you have a substrate, so I forgot that whatever it will be a 4-membered ring or 5-membered ring, but actually the in case of any cyclization reaction, exotate are favored. And what is exotate I will discuss later, but for avoiding this puzzling thing, I am writing a 5-membered substrate. So 1 2 3 4. So let's say this is your substrate, and now you react it with NBS, right? So what can happen in this case, this NBS can act as your brominating agent, and first of all you are getting this bromonium ion. So this acts same as your iodine, right? So now you have this one, and it can attack here to give you this lactone. So 1 2 3 4 5. So in this case you get the 5-membered lactone. I write it because I forgot either 4-member or 5-member will form. So to avoid this I am writing this, and this is how you get this 5-member lactone. So this is another function of NBS. Now lastly I will discuss one reaction which came in CSIR exam 2000 2017, I think it's June, right? So the reaction was given, actually it is a very simple reaction, but you have to know one fact, otherwise you will not do it. And in fact I did mistake in the exam. So you are given with this one, and then they give NBS. So here nothing is special. Allylic positions are there, and they used NBS 2 equivalent, right? So what will be product? And in the options it was given like bromine, one bromine here, one bromine here. This was one option. In other option it was given that two bromines are in the same place, and other options were given where bromine is there or there. But you know these reactions will not occur. Either two options may be correct. Either two bromines are in same allylic position, or they may be in other allylic position. Now in the first step, when one equivalent of NBS is consumed, you will get this, right? And if you follow the mechanism after that, another radical will be generated, and the chance of forming radicals are two. Either these hydrogen, so either the next Br dot arrived from the other NBS can abstract this hydrogen to yield this radical, or it can give you this radical, right? Two possibilities are there. Either the radical can be formed the same carbon where the bromine is there, or it can be formed on the other carbon where the bromine is not there. Now you have to know which stability of which radical is more, and then you can tell which product you will get. Now it is generally said that any type of substituents stabilize radicals. Either it may be electron donating group or it may be electron withdrawing group, right? So if you know this statement, you will say that this bromine has negative I effect, right? And that's why it is an electron withdrawing group, and that will stabilize this radical. But in this statement, this is actually a loose statement, and you should actually say that the electron withdrawal or electron donation, that must be resonance effect. That is, either it should be plus R effect or minus R effect. That is, the electron donation or withdrawal should be through the pi electron cloud, not through the sigma electron. That is, if you have electron withdrawing group and which withdraw electron through minus I effect, that will actually destabilize your radical, because radicals are neutral, but they are less, the carbon on which the radical is there, it is actually having the less electron than your octet, and that's why it is an electron deficient species. So if we classify, it is a electron deficient, and if you withdraw any electron from electron deficient species, that will actually destabilize your radical. And why the resonance effect group like oxygen, like OMe group, or electron withdrawing group like ester or carbon, why they stabilize your radical, I will discuss you later. But for that moment, you have to know that any electron withdrawing group which withdraws electron by its minus I effect, that will actually destabilize your radical. Now you can say that your bromine has lone pair, so it also has plus R effect. But if you know that the carbon, the radical orbital is 2p orbital, right? Or it can sp3 orbital, right? And it is 2s 2p. But in bromine it is 4p orbital, right? And the matching between these two is very weak, and that's why this plus R effect is very weak. So the bromine's minus I effect is much more powerful than its plus R effect, and that's why this radical is more destabilizing there, and you will get this radical. And I didn't know this before the exam, and I thought that due to the presence of bromine, it will actually stabilize the radical and I would get this product. But actually you will not get this product, and you will get this product. So bromination will occur into two different allylic positions. So this type of question was also in the model question paper for CSIR exam. So there is a high possibility of this type of question, and you should be careful while answering them. And more discussion about radical I will do in my other videos, where I will tell you why and how the electron donating or electron withdrawing group actually uh, stabilize your radicals. And for now, I think this video will be helpful for you, and if this video you like, then give a thumbs up and share this video with your friends, and don't forget to subscribe my channel for getting latest updates. So thank you.